All right. I'm talking to the recording now, but y'all can listen if you want to. Sorry, I ended the recording when I meant just to pause it. So now it's we'll be picking up from here and continuing our lecture today. We just had a pause to do the lab. So I'm going to pause again since there aren't any self. There. All right.
Oh, did you do the roll?
I do that at 5:45. And it's not 5:45 yet. Okay. And I do have a loudspeaker, just in case. What's that? If you want to turn it in, you certainly may. Okay. Or papers today, I think.
Are we able to see our grades for chapter 1 test?
What's that?
Chapter 1 test grades. Are we able to see?
At the end of the class.
You will give it?
Huh?
You will give it?
Okay, I can't return it to you because not everybody's taking
Just to see.
Huh?
Just to see grades.
Yeah, certainly. Okay. There are two questions that need to be addressed here. Now, let me hit both of them. We lost somebody. Are they coming back? Okay. All right. Well, I guess I'll go on and do this one. First thing that was asked, I was asking when I came back, is school open on Friday? Yes, it is. But it's not open on Monday. It's sort of a good news, bad news situation. The bad news is Monday's a holiday. The college is closed. There's no classes on Monday.
You mean next Monday?
Next Monday, coming up Monday. It's when we celebrate Veterans Day. The good news, though, it doesn't affect this class any because we meet on Tuesday and Thursday. So, yeah, that is great to hear. Okay. So we will be meeting as usual next week. Okay. Now, the next thing that was asked, if I can remember what it was, what did you just ask me? Oh, okay. If you want to see your test score from the first test, I don't have the second test graded yet. I hope that by Tuesday, most of, if not all of it, will be graded. But the first test is graded. If you want to see your test score before you leave tonight, when we reach, what time do we say? 6:30. Okay, when we reach 6:30, if you want to see your test grade, you can come see it. Okay? I'll have it up here at the front. I cannot return the test to you because not everybody has done the test. So please, the last two people, let's get the test done as soon as you can. Okay? Any questions about that? Okay. Good. And by the way, if you leave at 6:30 and you live close enough, you still have time to vote before 7 o'clock. Okay? So please do. Okay. That's the other advantage of quitting a little early tonight. If you haven't voted, hopefully you can. Huh? Well, I have no way of verifying. I know, but those can be taken off and shared with people, can't they? Yeah, and at my polling station, they forgot to give me one this morning, so that would happen. All right. Any questions then? So let's get back, and at 5:45, I will stop and call roll again. All right, energy conservation. Okay, we just saw in the lab what kind of energy was conserved down there? Mechanical energy. In general, total energy is what is conserved. And mechanical is a total between kinetic and potential, so that would be conserved as long as those are the only energies involved. But energy, total energy, is never created, nor is it destroyed. The total energy of the universe is the same as it's always been, okay? Never created nor destroyed. Energy can be converted from one form to another. We just talked about that before we went down there. We just saw it in the lab. It converts between potential and kinetic constantly, okay? But the total energy remains constant. An example of that is free fall. If I lift an object way up here, I've given it I've done work on it, given it gravitational potential energy. When I release it, then that gravitational potential energy becomes kinetic as it falls, picking up speed as it's losing its mechanical potential energy. Is gaining its kinetic energy. So therefore, it's gaining velocity. Okay. Now, energy transforms mechanisms. Two major ones: work and heat. Remember, I did work to give that object potential energy. Okay? As it fell, believe it or not, it was hitting air molecules, giving them minimal but slightly increased levels of heat. When it hit the floor and banged there, it actually gave more heat to the floor. That energy you had up here was converted once it hit the floor to heat. Not enough for you to sense, but there was heat nevertheless. If you had very sensitive thermistors or thermocouples or something on the floor, you would have measured an increase of heat down there. Okay. So, here, finally they get around to this. The potential energy lost when you released it from rest equals the kinetic energy gained as it fell, and there your mgh is equal to 1/2 mv final squared, because this is heat gained at the kinetic energy at the bottom equals potential energy at the top. This is where there is no kinetic energy. This is where there is no potential energy. So that's why we have to choose those. Solve for VF, the final velocity, and that's where we got that. Multiply both sides by 2, divide by m, the m's go away, and then you have 2gh, and then take the square root of it. That's where you got the formula we were using, as I gave it to you as well. Okay, any questions on that? Okay, now, here is the example, and why they have these pages apart, I'm not sure. But if you started with 10 meters of height, wow, 10 meters would be approximately a 3-story building. So if we were over there in that middle story where we just were, we were going up to the top floor and dropped down to ground level, that would be more like 10 meters, okay? Up here at the max height, all of your energy is potential energy. I like to say GPE, gravitational potential energy, because you're dealing with gravity here, mgh. And up there at 10 meters, if you had a mass of 1 kilogram, they didn't say this in the problem, but 1 kilogram, mass of 1 kilogram, G of 9.8 times 10 meters, that would be 98 joules at the top, right? mgh. The mass is 1 kilogram. The velocity is 0, so kinetic energy is 0, okay? Then, halfway down, it's lost half of its potential energy, but gained that same amount of kinetic energy. So it's down to 49 joules of potential energy, gravitational potential energy halfway down, and at the kinetic energy must now be 49 joules. Okay? The velocity there, height, square root of 2gh, this height, h of 5 meters, and you'll get velocity of 9.9. Okay? So halfway down, it's picked up went from 0 to 9.9. The other half down, it doesn't gain that much speed, but because every little bit it gains, the square of that is in kinetic energy. So at the bottom, 9.8 joules kinetic energy just before it hits. Not when it hits, but just before it hits. mgh down here is 0, as it is because you're down at your 0 reference level. Okay? That's why at the bottom of the swing, we're at the 0 reference level with 0 kinetic potential energy. All right. That's doing the same type thing we did in the pendulum. That's just like free fall, only it was on the string. Okay? Now, the next subtopic here is flow of energy. Okay? Now, this is a bit bizarre because earlier we had a subtopic that was the whole topic here was energy flow, and now it's saying flow of energy. It's really doing the same things, repeating a lot of what we just said. Again, energy is never created, never destroyed. It just changes form, converted from one form to another form. The total energy remains constant. Conservation of energy. For instance, the sun is producing nuclear energy constantly. Constantly. Those nuclear explosions are going on all the time, okay? Now, that little bit of that reaches our Earth enters our atmosphere as radiant energy, okay? That radiant energy hits the green leaves on the trees, and then the trees convert that radiant energy, electromagnetic energy of the sun, light energy, into stored chemical energy as they photosynthesize, okay? We partake of the green matter, whether we're eating salads, or whether we're eating fruits, or whether we're eating animal meat. The animals are partaking of the green matter. That's where they got their energy, that's where we get ours, and we convert that to more chemical energy, a different form of chemical energy as we digest our food, and then we either ride our bicycles or produce heat. And guess what? We're producing heat all the time. We're about 98.6 is our temperature. The room temperature is right around 70, okay? With the window open, maybe a little less, okay? But we're constantly giving off heat. That's where some of this chemical energy is going. At some point, that heat radiates back to the atmosphere. Now, that energy is hard to convert back to useful energy, okay? It does get radiated, but it's hard to convert it in one step back to anything that's very useful. Okay. So the next section in here, and this I think is the last section. Wait a minute. Yeah, we have already done that. All right. Energy sources today. And I do believe this is the last section. Nope, there's one more. Energy sources tomorrow. Okay. So energy sources today. Now this is an old graphic, so it probably isn't exactly correct, but at least it's ballpark. Okay? The biggest use of energy today is from petroleum sources. Almost 2/5. Okay, less than half, but 2/5 from petroleum. Now this is being pumped out of the ground in Saudi Arabia, in Iraq, in Iran, Venezuela, Nigeria, various countries, and the U.S. We are a fairly significant producer of petroleum. We used to have oil fields. We pump most of those dry. Where are we getting our oil now? We're fracking. What they call oil shale. You know, oil that is trapped in rocks. We're treating those rocks and pumping out the petroleum. Okay? There are also oil sands in Canada. They do a lot of that. It's kind of dirty, the oil sands are, but they still are getting it out. Now this one is going down, folks. It says 21% here, 1/5. It's probably less than that now. Okay? The advantages to coal was that you didn't have to pump them out of the ground. They were usually right below the ground. So they were easier mining, cheaper mining to do coal than it was pumping out petroleum. But coal was a far dirtier source of fuel, but not only dirtier, it was less efficient. Okay? That's why coal is on the way out now. Natural gas, this one I'm pretty sure is right here. It's still exceeded coal. Now it's even more so. Okay? Very few homes are heated with coal anymore, right? Maybe a few in some third world type countries, possibly. Maybe a few in the U.S. and other first world countries, but generally not. Natural gas is what we use at our house. You know, we get Alagasco provides natural gas in through pipes. we use it, okay? But not just that, the sources are there. When I was saying fracking, much of that is natural gas. Some is petroleum, but some, more of that is natural gas. So we have gone to that big time. Generation of electricity used to be largely coal, okay? Now more natural gas. So this one is shrinking, this one's expanding. Now the nuclear. That had been expanding up until disaster happened in Ukraine, Chernobyl. And shortly before after that, near disaster happened on 3 Mile Island here in the U.S. Chernobyl was far, far worse. In fact, it's still awfully bad. Okay, 3 Mile Island, we got it contained and controlled because we had a lot more safety mechanisms in place. They didn't in Chernobyl, and it was a total disaster. But even after that, nuclear kept expanding. Japan had almost no petroleum, so they had to import all their petroleum. They moved over to nuclear and built nuclear power plants all over the islands. France was another big user of nuclear energy. Lots of other countries really started expanding the nuclear power. So that may have gotten a little bit more than 8%, but it didn't get much more than that. What happened recently that sort of shut a lot of that down? Yeah, Fukushima. That was the earthquake off Japan that created the tidal wave. And of course, where was their nuclear power plant located? Right on the fault line. And so the earthquake happened there, the tidal wave happened there, completely swamped the plant, and therefore they had almost as big a disaster as Chernobyl, but without nearly the consequences, because they really had their safety in place. But Japan, that scared the daylights out of them. They have been going backwards on nuclear, going back to other sources, not nuclear. It's really shut us down. Here in the U.S., after 3 Mile Island, I don't think there was another new permit issued for nuclear power until the last few years. I happen to know that one was started or is in the process of being started, and that's at Plant Vogel in South Carolina, Georgia, right on the Savannah River there. The reason I know that, we live in the county in Georgia. You know, we have property in the county in Georgia where that Plant Vogel is located. They had, I think, 2 reactors. They opened the 3rd. So nuclear is very slightly coming back a little bit. So this may actually be a little bit more than 8% now. I'm not sure that it is. Biomass. What do we mean by biomass? What would be biomass energy source? What do we mean by that? That's burning any kind of, okay, petroleum is what? Basically, when it comes from the ground, what is it? It's crude oil, right? Crude oil, okay? Has to be refined quite a bit to make gasoline or fuel oil or something else like that, diesel, whatever. It takes a lot of refinement to clean it up quite a bit. What biomass would be is anything that's living that we're using as a fuel. Here's one example. Now, this is a major one, but it is one. All these restaurants use oils, cooking oil. Those are usually soybean oil, peanut oil, palm kernel oil, corn oil, some type of oil, okay? Well, once they're finished cooking with it, it's still oil. It's not nearly as dirty as crude oil is. So what they can do is sell that to a petroleum company, and they can convert that. That's not fossil fuel, that's current biomass fuel. There are other things that could be used, okay? I don't know that many people are doing it, but why they're not, I don't know. Rather than dumping trash and garbage into a landfill and covering it with soil and letting it sit and stew there for the next 10, 20, 30, 40, 80 years, I don't know. Nobody can use that land. No one wants to use that land. It probably still stinks. Why are we not converting that to natural gas. We could. There are what they call anaerobic digesters who could take much of our trash and convert it to natural gas. There was a proposal in the city of Birmingham somewhat shortly after we moved to Birmingham, which was quite a few years ago now, and a company was going to do that to people. No, it may blow up. We don't want it in our neighborhood. So they moved on and went somewhere else. But that's something I think we should be doing big time. Okay, we're not now, but we are using some biomass. Hydroelectric, okay? Alabama probably is far bigger than this in our percentage because we have fantastic lakes and dams across the state. Smith Lake is a hydroelectric plant. I think Wilsonville or Wilson or something like that is one. Huh? Lay Lake is? Yeah. Oh, that's in Wilsonville. Okay. They're all over the state. Gunnersville, Lake Gunnersville. That's a hydroelectric plant. They're all over the state. But there's not much room for any new ones because we've dammed up the easy to dam up rivers, and the rest of them, either too many people live along them that we couldn't buy the land, or they don't have enough drop in them to make it worthwhile. Other, this would include geothermal and solar. That's 0.5% here. My guess is that's quite a bit bigger now. Okay? What are we using? Solar is one, but another one that is not even mentioned on here is they have these farms all over the place, not much in Alabama. Yes, wind turbines. Wind turbines. They call them wind farms. When my wife and I, she had professional meetings out in Park City, Utah, which is near Salt Lake, and it was right at a week in between terms, so I got to go with her. So we went out a few days early and drove around to see some area out there we hadn't seen before. And we drove through parts of Idaho, Montana, and Utah. Huge wind farms. And the good news was the farmers were actually beneath those turbines because they're way up in the air, and they were still harvesting hay or whatever. They were still using their land, but they leased the turbine to the thing, so they were getting double income off their land. So this is really growing. That would be under other. They don't even mention wind. Solar, we're getting better and better at this all the time, but look, it's such a small percentage. How much is it going to take before we start replacing any one of those? That's the big deal. Okay, so anyway, that's how we're using now. It wasn't that many generations ago that we weren't primarily using wood for our heat. Okay? And wood for all sorts of things. Remember the old railroad engines? They were stuffing those things with wood. Pretty dirty, pretty smoky, pretty ashy, okay? But they did. Later they converted to coal, which was cleaner in some ways than wood was, less ash, and more efficient than wood, but still pretty dirty, okay? Then they converted to petroleum. The more we got into industrialization, the more we tried to improve things. Now, but if you look at this, natural gas, coal, petroleum, and even your biomass here, 89% can be traced to photosynthesis. Those little green leaves out there, photosynthesizing away, taking that energy from the sun and storing it chemically. So that would be 40, 61, 84, and 3 would be 87. They say 89, I don't know where they get. I don't think these two match up too well. But anyway, same ballpark. Now, what's our uses for this energy? Well, about a third of it is burned just to heat our homes and our businesses and our classrooms and things like that. Now, when they say heating, we nowadays use it for cooling as well. Electricity is used for cooling purposes, but that has to come from an energy source. 2/3 are burned in engines and generators, as in producing the electricity, okay? and producing your power plants, your anything that is using energy to do a process. Any engine such as that, making steel, or anything like that. Okay. So let's look at each of those sources separately. Petroleum. Now, the old days, they drilled into the ground, they had to drill really, really, really deeply. But when they did, if they struck oil, then it came, you've seen the movies and stuff, came gushing out of the ground, and they captured it and then started processing. Nowadays, most of that's gone. That's easy. That's sort of the low-hanging fruit there. Now we're having to get it from oil-bearing rock. And that's where the other came from, too, but you have fewer pools of it down there. So they have to get it out other ways. Where did it come from? What do we mean by organic sediments? Things that were once living. So this is mostly plant, but it could be animal, and animal waste, and things like this. Organic sediments transform over time. Now, when they say over time, they mean a long time. Millennia, thousands of years, okay? Now, that transformation occurs for several ways. Bacteria, as I said before, when I said anaerobic digestion of waste, that is bacteria that are consuming it, digesting it, but without air. Okay, that's what the anaerobic part is. Okay? Now, also after the bacteria have finished with it, or maybe while they're still doing it, it's under enormous amounts of pressure and enormous temperatures, because they're way, way, way deep there. So all this happens to convert over long periods of time that organic sediment to petroleum. The natural gas formation is very similar, so they're not going to do a separate one for that, as petroleum, except generally at higher temperatures, okay? And natural gas usually comes out cleaner than petroleum does. Petroleum still contains pretty high amounts of sulfur particularly. That's the main nastiness there. Natural gas has very little sulfur in it, okay? Petroleum and natural gas often are found together, okay? In fact, the natural gas, they used to, because they didn't know how to use it, they just burned it when it came up and then used the petroleum. Dumb, but that's what we did. Even today, I don't know if it's still there, but I remember when I was working at Shelf State, probably 20 some odd years ago, I drove out by Tarrant, and there was a coke plant, I think it was, had a big pipe, chimney-like thing that just was always in a flame. They were burning that waste natural gas because they didn't have any decent way to process it, and they didn't want it to build up pressure and blow up or something. Goodness gracious, couldn't you think of something to do with it, and use that rather than just burning it in our atmosphere? I don't think it's there anymore.
It is there.
It is still there. I guess there's a reason for it, but I don't know what that reason is, okay? Seems like they could use it, yeah. I'm sorry? Call roll? Okay, is it time? Yes, it is. All right. Let's get the roll call. Nice little break here. Okay, Isaac is still here. Ty is still here. Gary never made it in today. I doubt if he will. Michael's still here. Dalton's still here. Colton didn't make it in today. And Stestia is still here today. Okay. Hunter is still here, right? Where? There. Okay, got it. Oh, so I'm on the wrong way. Melanie, I forgot Melanie. Melanie's still here, and Stephanie's still here. Hunter's still here. Still in the marquee. Tyler's still here. Jersain is still here. Yep. Justin is still here. Yeah, there you are. Okay. Trent's still here. He had me call roll. There he is. Okay. Dimitri left, didn't he? Okay, so he's not still here. Jose's still here. Cody's still here. Patel's still here. Taylor. Is Taylor still here? Did we lose Taylor? Okay. He was here earlier, wasn't he? Okay. But we lost him. Peyton's still here. Okay. Chase is still here. Mac hasn't made it in today. Zachary hasn't made it in today. Kevin hasn't made it in today. Steve is here. Is it Steve or Stephen? Steve? Okay. Huh? Stephen. Okay. I didn't circle the end. Sorry. Okay. Spencer is still here. Brian is still here. Raina didn't make it in today, and Sarah still here. All right, good deal. Got that. All right, and recorded there also. Okay. So petroleum and natural gas often occur together. Supplies are limited. Now, we don't act like they are. We act like we can still keep drilling. And sure, we found more and more sources. We think we have found some others we haven't tapped yet. But guess what? They're still limited. Okay? Remember what we said? It takes millennia to make these products. Okay? That means we're burning fuel now that got made thousands of years ago. And we're burning it at a pretty fast rate. Guess what? We're going to use it up at some point. We don't know what that limit is, but they are limited. Used to be, we drilled into the ground, got the gushers, and used it. Now we're drilling miles below the surface of the sea to tap places there. Do y'all remember what a hazard that could be? Do you remember? What was it called? Deep Sea Horizon, wasn't that the name of the company? And boy, did we ever have a mess there. That lasted for months. They were losing that into the Gulf of Mexico. We still don't know if there's any permanent thing. The Gulf of Mexico recovered fairly well, we hope. Okay, but boy, that was a mess. Now, when this was written, over 50% of our petroleum was imported. Nowadays, we're less than 50% imported. We are manufacturing more. I heard someone say more than Saudi Arabia is. I find that really hard to believe, but maybe it is true. It's just that they sell it to other people because they don't have much of an economy themselves, except that we use it ourselves, so we don't sell it that much to other people. So there's petroleum. Coal, the next one. Actually, natural gas is next after petroleum, but we've already mentioned natural gas. Coal is accumulated also from plant or organic materials, processed over time, again, millennia, probably, by pressure and temperatures. They left off the bacteria here, but they were involved with it there too. And here's the progress, the progression that they do. Have y'all heard of peat bogs? Okay? We don't have many around here. Most of our materials like this, we lose the carbon dioxide into the air. But I bet you down in the Everglades or Okefenokee Swamp in Georgia or places like this, maybe the Great Dismal Swamp in North Carolina and Virginia, they still have some peat bogs there that the stuff isn't oxidizing away, and that peat over a long period of time changes to a mineral called lignite, which then ultimately goes to sub-bituminous coal, which ultimately, after a long, long period, will convert to bituminous coal. Okay? We do a lot of coal mining here in Alabama. Do we do bituminous coal mining? Unfortunately not. Most of our coal is way too dirty for that. Too much sulfur in it. And that's called, I think it's called anthracitic coal, anthracite. Not nearly as clean as bituminous. We still mine it. What do we use it for? We don't. We ship it down to South America or somewhere in Asia or somewhere else. because they're on a different planet, and when they burn it and it messes up the atmosphere, it doesn't bother us any, does it? Not immediately. It still will. Okay. Now we import most of our coal that we use in our power plants from Wyoming and places like that where they have bituminous coal. Okay. They don't have very big populations out there, so they don't use all their coal. They send it to us. We buy it from them. Now, there's lots of impurities in coal. There's quite a few in petroleum, way more in coal. Because coal is basically taken from rock again. There are minerals that don't get burned, and they turn into ash. That ash gets distributed. Sometimes that ash is pretty bad stuff too. Zachary is here. Okay. The last vehicle I had before the one I've got now, where I took it in to have service, was the same place we bought it. And there was an old guy who would drive me to work after I took my car in. And I enjoyed talking with him so much because he had been around a long, long time in the area. And he talked about when they would blow the furnaces, I guess you would say, at the steel mills to get the ash off of the piping that conducted the heat, okay? He said that the women knew not to have their clothes on the line on those days when they were going to blow the ash off because everything got coated with it. And generally the clothes that were out, if they didn't get stained really badly, they got eaten up, by the acidity or the bad stuff in the ash. And had a neighbor, the first house we lived when we moved to Birmingham, I said, boy, the soil around here is pretty dark and rich looking. He says, it's probably all ash that came out of the sky. Of course, he was kidding mostly, but boy, it was a mess. We were a pretty dirty city at one time. They cleaned that up mostly. The sulfur, I keep mentioning sulfur, that leads to, when sulfur burns, like sulfur in the coal or in the petroleum, when it burns, it becomes sulfur dioxide. Just like when carbon burns, it becomes carbon dioxide. So sulfur becomes sulfur dioxide. Guess what happens when sulfur dioxide mixes with water? Let's do a little chemistry here. Okay? SO2, that's sulfur dioxide, plus H2O yields H2SO3. Anyone know what H2SO3 is? It's sulfurous acid, which is next to being sulfuric acid. That's pretty bad stuff. That's why clothes fell apart, when that ash landed on it. Okay? It is a pretty bad pollutant. Okay? So most of the coal burning plants, okay, I know politically this is being talked about a lot, but most of the coal burning plants are having to clean up their discharge, or at least they were. And they have to get that sulfur dioxide out of the air. What do they use in cars to keep the sulfur dioxide from getting out the exhaust pipe? Say again? Catalytic converters. Now that also, does that do anything to the nitrogen oxides, or do those get through? Do you know? Okay. But the catalytic converters are there mostly for the sulfur dioxide. Okay. Now, all of these three, petroleum, natural gas, and coal, are what we call fossil fuels. Why? Because the photosynthesis that happened to store the chemical energy in them happened, like I said, millennia ago. Multiple millennia ago. Over time, the whole time the Earth's been here, producing green plants and stuff, that's been building up, and that's where those are. Well, guess what? We're using them way, 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 way faster than they're being produced now. There is a limit, folks. We don't know what it is, but there is a limit. Okay? So there's coal. Now next is moving water. What kind of energy does moving water have? Yes, moving water. Kinetic energy, exactly. Now this is renewable energy. Renewable energy means every time it rains, okay, well, what happens? Let's go back to the basics. Most of the earth is covered with what? Water. The oceans, okay? The sun hits that water, which is most of the surface of the earth, and it evaporates the water. That evaporated water goes up into clouds, and some of those clouds move over land, and those lands, especially over mountains where it gets really cold, and that water comes out and then comes downhill. We trap it, and we use the gravitational potential energy of that water that's way up there, converted into electrical energy in our power plants. Okay? That's the process. But hydroelectric plants only generate about 3% of the U.S. total energy consumption. For a while, it wasn't bad. It was, in fact, pretty good, especially here in the southeast. We had a lot of poor areas. Those poor areas tended to be places where there was high fall in the land there, and that's where they built the dams, Gunnersville and Smith Lake and Lay Lake and some of these others. They built them there. They bought the land cheaply, and built the dams, flooded the land, bought it for people. But guess what? Once they got the lakes there, people say, hey, these are pretty nice. And they built big fancy houses on the lake. Okay? Well, now, rather than being a resource for generating electricity, they use mostly as a land enhancement. Okay? And in enhancing the land, when the power plants say, hey, we need more water when it's a drought to make more electricity, they let the lakes drop. And then the people with the big rich houses on the lake say, no, I don't want the lake to drop. And guess what? Money talks. Okay? And then less is generated there. Let's use something else. So the growth potential is limited by decreasing availability of these sites. Can they dam up some of the rivers down around Auburn, say, and make a hydroelectric plant there? If you think about it, Auburn is on a plain. Okay? There's not a lot of fall. If you dammed up a river there, it would cover acres and acres and acres and acres of land and still not have much fall to it. So you wouldn't get that much potential. No, down on the coastal plains, you can't effectively do that. You have to be at higher elevations like Gunnersville is, Lewis Smith Dam over in, what's that, Walker County? Right at the end of Walker in Winston County or so. Okay. So growth potential, very limited. There's not much place. Now, back when they built these, we didn't use as much electricity, so we were probably producing way more than 3%. But now we're using more, so we, even if we're generating just as much, which we probably aren't, but even if we were, the percentage of our usage is going down because we're using that much more. Nuclear, we've already talked about this based on nuclear fission reactions. Does anyone know the difference between nuclear fission, which we use in our plants here, and nuclear fusion, which is happening on the sun? Anyone know? Does anyone know? Okay, nuclear fission is when you've got big, massive atoms that you split into smaller atoms, and they release an awful lot of energy. Okay? Whereas nuclear fusion is when you have tiny little atoms that you fuse together to make new atoms, bigger atoms, and that produces even more energy. In fact, a nuclear fusion reaction produces like multiple times more energy than nuclear fission. Now, as I just described, big, massive atoms, think uranium, plutonium. Those are the two big ones. When they split in a nuclear fission reaction, you have lots of really nasty byproducts. Other radioactive material in huge quantities of radioactive material that sometimes can't be used. Uranium, plutonium, that's where you start. Okay? The heat is given off, the water is heated in the reactor, then used to produce steam. The steam is then used to generate, to turn turbines to generate electricity. That's the process. Okay? From this point on, it's just like a coal-fired power plant. You use coal to heat the water to make steam to turn the turbines. If you use a petroleum power plant, a natural gas power plant, anything, you're making steam. The moving water, you don't use any steam. Okay? That's how you generate electricity with nuclear power. Now, when we build our power plants, we've done a pretty good job of building in multiple backup systems to add safety, okay, to the systems. Russia did not do that. The Soviet Union did not do that at all, and therefore when Chernobyl blew, it was a disaster. But even with all our safety mechanisms in place, we still had 3 Mile Island, which was close to being a disaster. It was for people living around there, but not too much. Those byproducts of that nuclear fission, some nasty stuff, folks. Okay? And in Chernobyl, there's still huge piles of nasty stuff no one can even get near. In Fukushima, where they had the tidal wave induced disaster, there was some pretty nasty stuff left there. They did contain most of it. Chernobyl, no containment. Let me just give you an example of how bad Chernobyl was. If someone got a phone that could look up and see what the date of Chernobyl was, okay? Anyone get CHENOBLE or something like that? That may not be it.
April 26, 1986.
So I got 1986. 1986. Okay? Now, what's that?
It happened in
Okay. Yeah. It's a place in Kiev or in Ukraine. Okay? It was part of the Soviet Union. Okay? Now, there was a kid who I had in 2 courses of math here. Couldn't have been more than 19 or 20 years old. Okay, let's just say 20. I had him as a student here not more than 5 or certainly not 10 years ago. So he might be 30 now. 30 from 2020 to be 1990, right? Yeah. What did you say, 86? Okay. So he couldn't have been any, okay. So he was born at least 4 or 5 years after Chernobyl happened. He was born in Ukraine. Okay? When he was born, he was deformed. He had no arm, no right arm, okay, at all. I think he had a finger sticking out of his shoulder. Okay? He had hair lip, other problems, developmental problems, but a group of pastors from Birmingham had been bringing kids over to the U.S. from Ukraine so they could have at least a summer to develop somewhat normal. Because those living anywhere close to that plant, and people were moved way away from it, anywhere close, kids were still being born with deformations. 5 years after Chernobyl happened. 10 years after.
What do you mean by definition?
He had no arm. He was born with no arm. He was born developmentally not there. This pastor and his wife adopted him. They saw him in an orphanage, and because his parents gave him up, they said, we don't want him. So he was put in an orphanage. This pastor and his family fell in love with the kid, brought him over here. He was a bright kid. He was He was a wonderful kid. Smiled a lot, even with all his handicaps. And he was finishing, he was trying to get through his math at Jeff State and had trouble, so he came here and he managed to get through. But he was being a physical therapy assistant so he could have other kids that had, for some reason, lost a limb or something like that to show them they could do. This was years after Chernobyl happened. People who were conceiving children were still having birth defects because there was so much radiation in the area. I bet you it's still happening. Okay? It's bad news, folks. These materials, now what do we do with ours? We take them and bury them in a mountain in Utah. In as good a containers as we can develop. But they're going to be there for thousands of years still emitting radioactivity. Are our containers going to last those thousands of years? We don't know. You know, it could be they're going to start leaking at some point and maybe getting into groundwater and maybe polluting water for states around that mountain in Utah. We don't know. That's why they say the safety of nuclear power is controversial, because we always are going to have those byproducts. There was one time, shortly after we moved here to Birmingham, that there was a plan in place to ship that nuclear waste from the Northeast, where they had nuclear power plants, down to Greene County, Alabama, and put them in our landfills down there. That had potential for polluting everything south of there. Mobile Bay, everything south of Greene County, including the people who lived in Greene County, and destroying the health and the well-being there. Fortunately, they said the train was on its way and just got stopped before it got into the state of Alabama. It was going to come right through Birmingham and go right toward Greene County. Somebody had the sense to stop it and say, no, we will not allow it here in Alabama. So they moved it somewhere else, but, you know, where the people didn't object to establish. It's not good stuff, folks. I mean, it's good. It doesn't produce air pollution, but it can produce quite a bit of problems. Okay, how about energy sources tomorrow? That is the last section in the chapter. This begins on about page 80. Let me see if I missed. Yeah, I have skipped over some stuff. Okay. You know the graphic that we showed a little bit earlier? I'm going to go back to it. Hang on. That one. This has been updated now in your book. This is primary energy consumed by the U.S. source 2012. So that's already 6 years old, okay? But here's how this graph has changed. Petroleum in this graph that you see here was 40%. It's now down to 36%. Natural gas was 23. It's up to 27. Coal was 21. It's down to 18. Nuclear was 8. It's still 8. Okay? Renewable, that would be biomass, hydro, and, let me see if hydro is included there. Yeah. Biomass, hydro, and other, that would be 3, 3.5, 4%. No, 7%. 7%. It's now 9%. Okay? Improvement, but awfully slow. Awfully slow. Okay? So you see things are changing. I was saying when I was doing this that they've gotten better. These are old numbers. Those are old numbers, but these are even older numbers. So we are at least sort of moving in the right direction, but it's awfully, awfully slow. They have a little blurb here, grow your own fuel. Be sure you put fuel there. Okay. When I was at University of Georgia, working on my master's, and this was a long time ago, they had a bus system they ran through campus. It was a pretty big campus and helped people get from class to class. They had their own bus system that ran through campus. One of their buses was retrofitted, so it didn't use diesel, it used peanut oil. That's biomass, okay? And it smelled really good when it drove by, okay? If you had a really sensitive nose, you could tell when it was a peanut oil bus as opposed to the petroleum, the diesel bus. But it can be done, but that was still an expensive process. That was no cheaper than diesel. Diesel was still cheaper than peanut oil because that's pretty expensive raising peanuts. Okay. But anyway, that's what they're meaning, grow your own fuel. Oh, by the way, Brazil has almost no natural petroleum. So they were almost totally dependent on outside sources. So what did Brazil decide to do? They decided to grow soybeans and produce their own fuel from soybean oil. And frankly, I think they've done a pretty good job with it. But the downside of that, folks, number one, soybean prices went up. Soybeans used for feed for cattle and animals. So that price went up. So beef went up and pork went up and everything went up. That's all on the economic side. But on the other side, on the other side, they needed more land to plant more soybeans. So they started clearing and burning the tropical rainforest, which they had a lot. The tropical rainforest, folks, that's the place where most of the vegetation lives on the planet, and that's where most of the carbon dioxide was taken out of the air that we were pumping into the air, and that was a self-defeating process there. Because now the main source of cleaning the air, we were cutting it down and burning it, which is putting more carbon dioxide in the air. So it was just to raise more soybeans so they could produce biomass fuel. Not particularly great. So what are our energy sources tomorrow? Okay, wait. Let me keep on going. I skipped over page 78, which is a picture of the person behind the science. Excuse me. We've used his name a lot every time we talk about an energy unit. What is that? Joule. James Prescott Joule. Mentioned here in the text. Now, if you choose to write on Joule, this cannot be your source. You have to get your source from outside the book. This can give you ideas about it. Okay? They mention another person here in this blurb, Lord Kelvin, whose name actually was William Thomson, and he took Joule under his wing and promoted him big time, because back then, people from the common areas, Joule's father was a brewer, they were considered not good enough to be scientists. And they said, hey, this guy's good enough. Other people that were mentioned here, John Dalton came along before him. So you get several possibilities here in the places that you can, potential paper topics, let me put it that way. Okay. Other things that are mentioned, we'll be talking about this more in the next chapter. Joule developed what they call the mechanical equivalent of heat. For the longest time, heat was considered its own thing. It was not considered an energy form. It was considered an ephemeral substance. They couldn't trap it or anything, but they knew it was there. So Joule showed that no, work, energy, heat are all manifestations of the same thing. So, mistakes and misunderstandings, recycle or reuse, that's another issue you might address there. Now, finally on page 80, energy sources tomorrow. What are some possibilities? One that's different from those commonly used today. Well, it's hard to imagine, isn't it? We're doing things today that were hard to imagine 10 or 15 years ago. Sure, the concept of an electric car was there, but it wasn't considered very practical at all. You just couldn't get very far. Today, there's a car company, don't know if they're going to make it or not, Tesla, who's producing a pretty impressive car. Still awfully expensive, though. Okay? I think all the other car manufacturers have them on their planning drawing boards, don't they? No, GM does. I think probably Ford and others do too. Not too many years ago, I think it was probably Toyota who first came out with the hybrid car, and now just about all the companies have hybrid cars. So not too many decades ago, those were unheard of, almost unthinkable. Now, they're little steps in the right direction. Okay? So what are some possibilities? Today we're using mostly fossil fuels, 88% fossil fuels, coal, petroleum, natural gas. Nuclear about 8%, falling water about 3%, minuscule compared to fossil fuels. Fossil fuels will not always be here. We're using them up at a far, far, far faster rate than what they're being produced. So what are we going to use? Tomorrow, solar. Now this shows how old this book is. They don't even mention wind. Now you might say that's a little bit like geothermal, but that's not what they mean by geothermal. Solar, and you might say, well, it's sort of part of solar, but it's a different thing. And guess what? That's nothing new. The farm that my father bought when we moved to Georgia, when I was 4 years old, had a defunct. It wasn't being used anymore, but it had a windmill on it. That's how they used to pump water, was with a windmill. They didn't have electric pumps to pump water. They used windmills. But as soon as they got electricity and said, hey, not nearly as much maintenance on this, just buy your electricity and pump it this way, they quit using it. Now we're using wind again. Okay? Now what do we mean by geothermal? Anyone know? Geo means? Second? The earth. That's exactly what it means. And thermal is heat from the earth. Anyone think of what that could possibly mean? Okay. What comes to mind if I mention the nation Iceland?
Green plains.
Say again?
Green plains and people.
Can't hear it. What you say?
Green plains and people.
Green?
Iceland.
Why do you say green?
Iceland's green.
Are you thinking Greenland?
Yeah.
Okay. I said Iceland. Okay.
It's the ice cold one.
Okay, yeah, I think it's cold. Iceland, you think that's a really cold place. Okay, and it is. It is. Way north, way north. So you would think their heat bills would be enormous for people who live there, right? Excuse me. Wouldn't you think? Guess what? They probably have some of the cheapest heating bills on the planet. And here's why. Iceland is a volcanic island. Okay? And as a volcanic island, it has lots of geothermal energy. Those rocks are really hot. So what they do, they pump water over the hot rock, pump it through down beneath the ground into people's homes, under the floors. They do all their heating by hot water off the hot rocks. Their heating bills are next to nothing in Iceland, just paying for the energy to pump the water. And that's all. Okay? Now, hydrogen gas. Sounds like a good idea, isn't it? When you burn carbon, you get carbon dioxide, which is a greenhouse gas. Okay? When you burn petroleum coal, you get that, but you also get sulfur dioxide, which is acid forming. When you burn anything, you get usually nitrogen oxides, which are acid forming. Okay? All those are acid forming. What do you get when you burn hydrogen gas? What is hydrogen oxide? Water. You get water as a byproduct. You can't get much cleaner than that, can you? And hydrogen, when it burns awfully hot. It gives off enormous amounts of energy. Does the word Hindenburg ring a bell? What comes to mind? An explosion. What explosion was that? The blimp. The Hindenburg. It was called the Zeppelin back then, I think, or something like that. But it was over in Europe, and the lightest gas that we have is hydrogen. So it was the most effective in hot air, lighter than air vessels. And that was before we had airplanes. That was the only way you could fly. So they had the Hindenburg. But one day, and it's still not clear from what I understand of what happened, but either lightning struck or else the Hindenburg scraped against something and ripped it, and at the same time produced a little bit of heat or a spark or something, and it blew up. And great was the explosion there, because that hydrogen burned like crazy. Okay? Ever since then, what do we use for the blimps? Not hydrogen. The next lightest gas is helium. Helium doesn't react with anything. It will not burn. It will not react with anything. All blimps are now made with helium gas. It's heavier than hydrogen, but it's far safer than that. Okay? Another one that you mentioned, and here's the problem with hydrogen gas. You would think that would be a great thing to burn in the engine. In fact, at one time, we had a program here, an automotive program on renewable fuels or something like that. Do we have that still? And they were working on the concept of taking the electrical and the hydrolysis of water, capturing the hydrogen that came out of that, and then burning it later. So it wasn't netting anything, but it was cleaner. Because it wouldn't net anything, it was hard to do, so I don't think they do it anymore. Okay? But it was an effort. Okay? Here's the problem with hydrogen. It's the lightest gas there is. It's a very, very reactive gas. That's why it burns so easily. It's the smallest molecules. It takes up a huge amount of volume. So in order to use hydrogen gas, you have to do a couple of things. Either have huge tanks of it, and then you have to haul around these tanks, and that's a lot of weight, and you don't get a lot of good out of that, or else you pressurize it. Well, that makes better. Your tanks are smaller, but you pressurize it. But when you pressurize it, it tends to want to leak. And because there's no product made that's going to contain all the hydrogen gas, it's going to find its way through just about any material we have, okay? And because it's very explosive, if you have a leak, you could have an explosion really easily. So there's some problems with hydrogen gas, okay? What they're trying to do now, some of the fuel cells, they're trying to convert a material to hydrogen gas and then use it right away. So you don't have to store it, and you don't have to deal with pressurizing it or anything else. Now, like I said, back when we were talking about nuclear power plants, that's fission reactions. Splitting huge atoms into smaller atoms, and that releases an awful lot of energy. But I mentioned that the sun is actually fusion reaction. You're fusing two hydrogen atoms together and forming helium, which is a much cleaner process, far less undesirable waste material. But the only successful, this probably isn't quite right, but does anyone know what a hydrogen bomb is? That's where you do this. You set off a nuclear reaction that is actually fusion rather than fission. But in order to get enough energy to make a hydrogen bomb, and we have exploded them. North Korea claimed to have exploded them. I'm sure Russia exploded some, and possibly some in Europe. I don't know. Okay, but in order to, for us, the bomb we did, the fusion bomb we did, bombs go off simultaneously to get enough energy to make fusion happen, and then more energy was released. That's not very efficient, and you still have all the gas left over from the fission. So that wasn't very good. So what they're talking about nowadays is doing fusion on a much smaller scale. Again, sort of like the hydrogen gas ideal, a fuel cell, release it and use it immediately. And that's what we're going to try to do with fusion, but it's still a work in progress, in process. Okay? So let's look at some of these individual technologies. Solar. One is solar cells. Do any of you have any solar cells on you? Do any of you have an old calculator? Any of you have an old calculator? I'm not talking about your cell phones. An old calculator.
Sensor.
What's that?
Sensor of the cell phone. The sensors.
Okay, does that add up to it?
No, like the sensor detects the temperature.
Okay. The old calculator, right here is one. Right here. You know what this is right here? Light cells. It says solar cells, but it uses this light. And that's what powers the calculator. Your phones have that too? No, I didn't think so. You don't get enough. There's enough for a calculator, but not enough for a cell phone. Okay? So yes, it's direct conversion of light to electricity. Okay? The photoelectric process, I'm not sure, but I believe you came up with that one. I'm not sure, but I think you did. Other ways we use solar power is what they call power towers. There you're capturing the light from the sun, focusing it. Is it time?
Yeah.
Oh my goodness.
What time is it?
What's that?
What time is it?
What time is it? It's right at 6:30. Which means we didn't finish the chapter tonight, which means the test will not be Thursday. Okay? Yeah, we only got a couple more slides to go and that'll be it. So, 2 more pages. So we won't have the test on Thursday, but we will next Tuesday. So Thursday we'll finish this chapter, get started in chapter 4. We'll go 2 hours and 30 minutes, and hopefully get far enough to have a lab the last 2 hours. Okay. Okay. Not deep enough. Not deep enough. Not deep enough. Where are we now? Too deep? Too deep?
That's great.
Okay.
Oh, yeah.
What?
We just want to have 10 ready from chapter 1.
Oh, yeah, there too.
They never find.
All right. Isaac's not here. Ty's not here. Gary's not here. Michael's not here. Dalton's not here. Let me end this.